S. Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S. Chand Academy, and I am Anmol Bhatia. The course that we are doing is engineering mechanics, and concerning the rigid bodies, we will be dealing with the case of plane constrained motion.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
The topic is related to rigid bodies, and the problems that we will be dealing here are related to the constrained plane motions. So let us come to the case of constrained plane motion. So you might have came across this term. Let us first understand that what is this constrained plane motion. So majority of the engineering applications that involves rigid bodies, and those rigid bodies are moving under certain constraints, and those examples of those conditions are like crank or the connecting rod or the non-slipping wheels. Here it is basically it involves certain constraints while the components are in motion. So constrained plane motion is basically the motion with the definite relation between the components of acceleration of the mass center. So there is a relationship between the acceleration, but with that acceleration is with the mass center and the angular acceleration of the body. One such example is this. It deals with the acceleration of the mass center and the angular acceleration of the body. Additionally, we have the case of non-centroidal rotation in this particular condition. So what is this non-centroidal rotation? So it is basically the motion of the body which is constrained to rotate about the fixed axis, and it will not pass through the mass center. So this particular body is constrained to rotate about a fixed axis. So there is a fixed axis on which this body is constrained to rotate, but this do not pass through the mass center. And the relation that is particularly used, and that particular relation is a kinematic relation that particularly governs this acceleration and the angular acceleration condition. So this angular acceleration can also be represented, or this acceleration component normal can also be represented in the terms of angular velocity. So that would be r omega square. So what is that particular kinematic relation? It gives you a relation between the motion of the mass center g and the motion of the body about that g, which is the mass center. So mass center is this. It gives you two relationships. One is this acceleration, which is the tangential acceleration, and another is the normal acceleration. So normal acceleration is this an, and tangential one is at. So it is represented by r alpha. Alpha here is the angular acceleration, and r indicates the position vector, and this r indicates that position vector, and omega is the angular velocity. And the kinematic accelerations are basically these kinematic accelerations, or these particular relationships for at and an are particularly used or derived from those D'Alembert principles that we have already studied in our previous videos. So if you haven't watched those videos related to D'Alembert's equilibrium, you can visit the playlist of S. Chand Academy channel. So this is one of the example of the non-centroidal rotation. Now there is a case of this rolling motion. Constrained plane motions category also contains this rolling motion. So what happens in this case? You have a body whose mass is at a point g, and this weight is moving downwards, and additionally this friction is there into the picture, the normal component, and we are applying a particular force on the component. So while rotating, or while the body starts rotating, it undergoes a moment of inertia with the angular acceleration, and the force with which we are pushing this particular object that is equivalent to mass into acceleration, and this also moves in the same direction. So what happens? So for the balanced condition, this x equals to r theta, or you can say that the angular acceleration is equal to the acceleration equals to r times the angular acceleration. For case of this rolling friction and there is no action of sliding, this force is less than equal to mu times n, that is basically the reaction force. So mu multiplied by n is that particular force that should be lesser than. And in that particular situation, when there is no sliding, you have to keep in mind that this relation is true. And if there is a sliding action and that sliding is impending with rolling, so F is equal to mu into N. And if this rotating and sliding action both are there into the picture, then this constant changes. So mu s changes to this mu k term, and this acceleration and r alpha are the independent terms, and they do not depend upon each other. Rather, in the previous situation, they are dependent. So for the geometric consideration of that particular body, and if it is moving about a particular point, so this geometric center of that unbalanced disk, if it is there, so it depends, or it also undergoes this particular formula, and that formula is a naught equals to r into alpha. And if you want to find out that g, associated g for the corresponding acceleration, so that would be a naught plus ag slash o, and ag slash o can also be converted or can also be interpreted in terms of tangential and the normal components. Now let us come to certain problems which involves the same concept. So here is that problem. It says that there is a uniform sphere of mass m. So we have a sphere which is of mass m with the radius r. The sphere is having that mass and the radius, and it is projected along a rough horizontal surface with the linear velocity v. The velocity is mentioned, mass is mentioned, radius is also mentioned. Coefficient of kinetic friction between the sphere and the surface is mu k. So mu k is one of the coefficient which is mentioned, and it is given by mu k, that expression. What do we need to determine? We need to determine the time at which the sphere will start rolling. So we wanted to find out the time with which it starts rolling. That means initial time period is required, and without sliding, and linear and angular velocity of the sphere at that particular time period. So we have seen that particular case of with sliding, without sliding in our previous explanations. Now we'll apply that particular thing in this particular example. So as far as the solution is concerned, we need to make the free body diagram of that particular case. So you are having that spherical object which is having that g as the center, and from there the weight is suspended in the downward direction. So the two components of the forces, one, the normal force and the tangential force, are acting on the surface. Additionally, it is equivalent to this rotations, in which you have this force component which is mass into acceleration, and additionally you have this I into alpha case, which is the moment of inertia and the angular acceleration category. So what we will do, we will be solving it by using the general by using the general methodology, in which we take sum of all the forces in x direction and we put it equals to 0. Sum of all the forces in y direction, we put it equals to 0, and also the summation of all the moments, and that is also equivalent to 0. So sum of all the forces when it is equivalent to forces in y direction, and that is equivalent to 0. So you can see that you have two forces, one is N and another is W. Both of the forces are in the opposite direction. So we have N minus W, and that is equal to 0. So from there we can interpret that N equals to W, where W equals to mg. So the normal force is equal to mg. Additionally, we have to use the sum of all the forces in x direction equals to 0. So the force in x direction is this force, which is F, and that is equivalent to that MA part. So this is in this direction, MA is in the right direction. So we have taken, or we have taken this assumption that the forces on the right hand side is considered to be positive. So minus F equals to MA. So we will be substituting that particular value. F is mu into mg, and that value is equal to that acceleration. So m and m gets cancelled out. So acceleration is equal to minus mu k into g. And thirdly, we have to incorporate the usage of all those movements. So sum of movement is equal to 0. So first movement is the reaction force, which is there. So the rolling force, that is equal to I into alpha. So that rolling force is equivalent. So this rolling force is mu mg multiplied by r, F into r. And that is equal to this I into alpha. I, in case of this, this sphere, that is equal to 2 by 3 mr square into alpha. So on solving, you'll get the value of this angular acceleration. So this movement is force into that distance is mentioned. So force into that distance is with which it moves. So force into that distance that we have assumed as r, and this alpha indicates the angular acceleration. So we got these three things, and additionally we have to apply those kinematic relationships in order to find out the velocity and that angular acceleration. So to find out velocity, we have to use the first kinematic relationship, which is v equals to u plus at. So in our situation, this initial velocity is v naught plus at, and that is equal to v. So v equals to v naught plus at. So v naught plus acceleration we have already calculated, which is minus mu k into g multiplied by t. And similarly, for the angular one, we can replace this by this particular notation, which is omega equals to omega naught plus alpha into t. So we can substitute this omega naught plus alpha into t. Omega naught initial value of this angular velocity, that is equal to 0, plus alpha we have already calculated in the previous case, so we can substitute it. So these two we have already calculated from the previous part, and we have substituted it in this expression. Now we have to find out that particular instant t. So we have to use this formula, which is v equals to r omega. V already we have, which is v naught plus this value, and omega we have calculated, and this omega is in terms of t, so we can replace it by t1. On solving, we'll get the value of t1. Once we obtain this t1 value, we can substitute it in this omega term. So we'll get this omega 1 value, and additionally when we put this omega in this formula of v1, we can get the value of v1 also. So v1 is obtained, omega 1 is obtained, and t1 is also obtained, and that was particularly required in the question, that you can see that initial time frame was required, the linear and the angular velocity of that particular time frame. So what we have done, we have used the normal methodology. And what is that normal methodology? We have substituted sum of all the forces equal to 0, and we have substituted sum of all the movements equal to 0. On solving or putting in the values, we will obtain this t term, omega, and that velocity term. Now let us look at another problem, which is sample problem number 2, that is related to the same concept. So it has 2 gears, and one is fitted with this particular handle, and the radius is mentioned. So we have all the values of initial part, which is mass for this E component, this distance is also mentioned, and mass for the another component is mentioned, and you are given with the portion AOB of the mechanism is actuated by gear D. AOB, this mechanism is actuated by this particular gear at an instant which is shown by the clockwise velocity, which is 8 radian per second, and the counterclockwise angular acceleration is mentioned. So you are given with the angular velocity value, you are given with the angular acceleration value, and you need to find out the tangential force which is exerted by that gear D and the components of the reaction at the shaft O. So you have to find out two different cases. So how to solve it? You have to draw the free body diagram concerning the same concept. So what we can do, we can use that particular equation or particular diagram which indicates that the gear AOB is there, and there are several set of forces. So one force is this WOB, another force is that reaction force. This X direction force is there. WE is the weight of this particular gear and a tangential force at a particular distance, which is equivalent to that inertial force components and the inertia force into that acceleration component which is there. So you are given with certain values like ME or the distance value and OB and the angular acceleration and the velocity component. So after drawing this free body diagram, what we can do, we can particularly find out what is the value of WE from here. So WE can be found from the mass. So mass is mentioned to you as 4 kg. So 4 into 9.81, that gives you the value of WE. And WOB is the mass of that component, this component. So it has that mass value of 3 kg. So 3 into 9.81, that gives you 29.4 value. So we got the two values of the weights, or you can say the forces. So these two values are obtained. One is WE, another is WOB. Now I need to find out what is the value of this IE into alpha. So IE can be calculated from this MR square, which is MKE square multiplied by alpha. So I have substituted all these values and obtained this. And then this movement, which is M mass of OB, and acceleration, which is related to this OB component. So acceleration can be written in terms of that alpha or the angular acceleration component, which is R alpha. So we can substitute those values and calculate MOB in tangential direction and in the normal direction, and additionally IOB into alpha can also be obtained. So we got IOB alpha, we got IE into alpha, and this MOB into tangential component and the normal component. So what we got after putting in the values of the basic calculation, we got WE, WOB, and we got this IE into alpha. Then IOB into alpha, the normal component and the tangential component by substituting all these values. Now what to do? We have to go with the general methodology, and that general methodology is putting in sum of all the forces in x direction equals to 0, in y direction equals to 0, and all the moments. So you can see the first moment is related to this force which is there multiplied by the distance. So this 0.120, the tangential force multiplied by that particular distance, that is equivalent to all the moments which are there in the system. So IE into alpha is one of the moment, MB into O tangential moment, and this IOB into alpha. So putting in all the values, we can get the value of this F, and then we have the sum of all the forces in x direction equals to 0. So in x direction, we have this reaction force, and that is equal to this tangential component, which is this component MOB into AOBT. So we have substituted this value so that reaction force can be obtained. Reaction force in x direction can be obtained. And thirdly, this Fy component was required. So Fy is equal to 0, sum of all the forces is equal to 0. So herein we have to check all the vertical components of the forces and put it equals to 0. So on solving, we'll get this y component. So we got the x component, f component, and the y component after substituting all the values, because those values we have already calculated, like WE we calculated, WOB we calculated, and that f value is also obtained. The question was demanding tangential forces exerted and the components of those reaction forces. So components of those reaction forces are Fx, Fy values, and that tangential force component we have already calculated. So this tangential force component, which is this force component which was be exerted on this gear, that we have calculated, and the reaction forces we have already calculated. So we stop here for a short break. After coming back from the break, we will understand this concept of rigid body which is there with the constraint motion in detail.
Now, quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break. Before going to the break, we have understood the concept of rigid bodies concerning the constraint motions. And we have solved two problems which are related to the same concept. Now we will be understanding that concept more with the help of some numerical problems. So we'll be dealing with sample problem number 3 in order to solve that, understand that particular concept. So what is this particular problem and how it is different from the previous problem that we have seen? In the previous problem, before going to the break, we have that base which was a horizontal surface. Now this surface is not horizontal surface, this surface is an inclined surface, and this disc which is there is a spherical shaped disc. So you can see that there is a sphere of weight W. It is released from the particular part with a particular velocity, and you can see that it is written that it has no initial velocity. So initial velocity is 0, and it rolls in the downward direction so that it gets an inclination of 30 degree. Now we need to determine that minimum value of coefficient of friction, velocity of G after the sphere has rolled 3 meters. So there is a distance mentioned to us, and the velocity of G if the sphere were to move 10 feet down a frictionless incline. So we need to calculate all these three terms. So how can we do that? Initially, the approach to solve that problem is to create a free body diagram. After making a free body diagram, we have to analyze some of all the forces in x direction, in y direction, and we'll calculate the moments also and put it equals to 0 so that the force components or the moments can be easily calculated. So what we will do, we will create a free body diagram of the same sphere. So we have this sphere and the two force component, one is the tangential force component, another is a normal force component that is acting on the surface, and the weight is no doubt acting downwards in inclination with theta. And herein, if it is equivalent and it is moving, so it would be equivalent to another body, it would be equivalent to the body with mass into acceleration and I alpha part which is there on the surface. So this inclined diagram is to be created, but this W would have two components, one which is W sine theta and another would be W cos theta component. So herein we will do sum of all the movements which is equivalent to 0. So what we will do, we will create this W sine theta component. So the vertical component of this would be the W sine theta multiplied by the distance it traveled, and MA is this force component multiplied by this distance it traveled plus the movement. The movement is I alpha. So putting in the values like R, we have multiplied it here, mr alpha into R plus I's place we have to write 2 by 5 mr square into alpha. So on solving, we'll get the value of this acceleration component in terms, and A acceleration is equal to R into alpha. So we can substitute this value so that this acceleration component can be obtained. So acceleration component can also be determined from there. So one part is obtained, which is the acceleration value. Then we have to go with sum of all the forces in x direction and in the y direction, and we need to put it equivalent to 0. So one force which is there in the x direction, that would be W sine theta, minus the frictional force which is in the opposite direction. So minus this F, and that is equal to MA. So we will be substituting the values that we obtained in the previous case, and after substituting in the values, we will get the value of this force in terms of W. Then we will go with the sum of all the forces in y direction, and we need to put it equals to 0. So the forces in y direction is this N, the cos component of the W, and here we do not have any y component or the vertical component, so we need to put it equals to 0. So N would be equal to this constant multiplied by W. So we got two components together. Now we know that F equals to mu into N, and because it is sliding on the surface, so it would have the sliding friction there. And acceleration, I have already told you that we have calculated. So in solving, we can get this value of this mu s. So what we get the value of this mu s component, and W was not given to us in the question. If it is given, then we can substitute that value directly. So next, the question demands that we need to calculate the velocity after 10 feet of the uniformly accelerated motion. So we need to use that formula, which is the kinematic formula, v square minus u square equals to 2as. So we have two components, two forces. One is the final velocity, another is the initial velocity. So initial velocity is mentioned to us that it had no initial velocity, so 0, plus 2 into acceleration we have already calculated, and the distance is mentioned to us, 3 meters. So from there we can find out the final velocity. Now if there is no friction, then the linear acceleration was to be determined, and that determination will be with the 10 feet value. So what we will do, we'll put the sum of all the moments equivalent to 0. So here we have one moment which is I alpha, and we need to put it equals to 0. So acceleration value comes out to be 0. And sum of all the forces in x direction, if we need to put it equals to 0. So from there acceleration can be determined. Additionally, if we can substitute this acceleration value in this expression, we'll get that another value of the velocity. So we'll get the two velocity components depending upon the two different conditions. One condition was there with the case mentioned, and the second condition is there when there is no when there is this part, when it is equivalent to 0, when there is no value of acceleration, so acceleration becomes 0. Now we'll come to another problem in which you would get an idea of the combination of those two concepts. So basically in the previous two problems, what we have seen, one was a sphere which was rolling on the surface, and the surface was horizontal. In the second case, the sphere was rolling on the surface which is inclined at a particular angle, and it has certain conditions. Now in this particular example, you will come across two different spheres, and a cord is wrapped around its surface. So you can see that the cord is wrapped on the inner hub of the wheel, and it is pulled horizontally. So this one is pulled horizontally, and the two radiuses are mentioned. And the force is also mentioned that it is 200 Newton. Wheel's mass is mentioned 50 kg, and the radius of gyration is also mentioned. Knowing that this mu components are there, you need to find out the acceleration of g and the angular acceleration also of the wheel. So two components are required, acceleration and the angular acceleration component. So herein, when the radius of gyration is mentioned to us, we need to find out the value of this moment of inertia. So how to calculate that moment of inertia? That depends upon the radius of gyration. So I equals to that formula, which is mk square. So 50 is that mass, and k value is this. You can substitute that value and you will get that moment of inertia. Additionally, when we assume that there is no slipping, because we are pulling that rope from the surface, when there is no pulling angular acceleration or this acceleration component can be obtained from the angular acceleration. So r into alpha, r is mentioned to us and alpha we can calculate. Now what we have to do, we have to go with the forming those equations in the standard notation form. So we can substitute all the movements equal to 0, forces equal to 0, and forces in the y direction and x direction equivalent to 0. So on clubbing all these values, we'll get those acceleration component, we'll get that force component, and additionally we'll get that normal force component. So on substituting all these values, because we have those values, substitute the values and you'll get this component. Now there was some conditions mentioned in the question, that the tangential reaction to the maximum possible frictional force. So if we need to find out that maximum frictional force, that is equal to this mu into n formula, and when there is rolling and there is no slippage, we have discussed that part in the previous theoretical concept, that f should be greater than this f max. So this f max is there, and f we have already calculated, which is this component, and this component says that this f value is greater than this f max, and that is there without slippage. And thirdly, this calculation which is with slippage. So with slippage says that f equals to mu k into n. So mu k and mu s, both the values were there with us. So 0.15 into this value, so 73.1.6 Newton is the final result. And lastly, we'll substitute sum of all the forces equal to 0 and moments equal to 0, so to get the final expressions of this acceleration and alpha value. So we can get these values by substituting the results. So with this, we come to the end of the video, in which we learned the concept of rigid bodies, constrained motions with the help of certain numerical problems. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the